In this video, we're going to really talk about Hooke's Law. Hooke's Law is our first formula in physics, so it's kind of exciting because you'll have plenty of formulas. If you look at the formula sheet, you can see that there's plenty of formulas that we'll learn, but this is our first one. In Hooke's Law, it just talks about the force that's exerted on a spring, and that force is equal to the spring constant times the distance that the spring is stretched. So if this is our equilibrium position, well, this actually, this is how far the spring is stretched when nothing is on it. This is when it's got a little weight, and this is when it would have double the weight. If you have a spring and it's just sitting here and that's its rest position, that max distance is that x. And the spring constant, this is something that is special to each spring. If you've got a trampoline, the springs on the trampoline are really tightly coiled and they're really hard to pull apart because you would not want a trampoline. Think if you had a trampoline like this and then you had a slinky here. Okay, these are the legs of your trampoline and you have a slinky right here. Okay, can you imagine if you jump down, it would like go all the way to the ground and that would really hurt. Okay? And it wouldn't really go back up, but because you've got this really tightly coiled spring on your trampoline, it only goes down just a little bit, and so you can bounce back up and you don't get hurt because it hits the ground. Okay, so this is a really tight spring. A slinky will have a completely different one. We'll have these really long ones that we'll use for our spring lab, and those have a completely different spring constant from the trampoline spring slinky or the regular slinky. So all springs have this spring constant, and it depends on the stiffness and some other properties of the spring, and it is completely unique for each spring. So your problems will say such and such has a spring constant of whatever, or they'll give you the force and give you the distance and ask you to solve for the spring constant. So here's just a little thing what's going on. We have our spring and it's at rest. This person is pulling the slinky down and then they're letting go and it starts accelerating upward or moving upward. Then it'll move up and then you can see it's still moving up. This is when it meets the rest again, and this is when it's gone all the way up, and once it goes all the way up, it's going to start moving back down again, and that's going to keep happening until it stops moving. The potential energy of a spring, this is different from our potential energy equation we'll do later. This is our second formula, and you can see it's 1/2 times that spring constant times the distance that spring moves squared. Now, the units of energy are joules. Okay, and so you do some math, you'll say the potential energy of a spring, and it is equal to whatever number that you come up with, joules. And this is equal to newtons times meters, and that'll be important in our conversions, and you'll see in that example problem. Okay, so our first example problem, we have a spring is stretched by 18 centimeters. Okay, this is a distance, so that's going to be our x. Okay, when a bag of potatoes weighing 56 newtons, newtons is our symbol for force, so this is our force, and so the potatoes are suspended from the end of the spring. And we want to determine the spring constant. And the spring constant is K. So here's what we have for part A. We have a distance of 18 centimeters. We have a force of 56 newtons. And we have a spring constant. And the units for our spring constant are newtons divided by meters. Okay? Now we see newtons divided by meters is our unit for spring constant, which means in order to get our answer to come out right in the formula, we have to convert these centimeters to meters. We cannot leave them like centimeters. It will not work. Okay, so we have 18 centimeters and centimeters is what we do not want anymore, so we'll put that on the bottom. Meters is what we do want, and we are going to ask ourselves how many centimeters are in 1 meter. If you guys remember, a century is 100 years. And so there's 100 centimeters in 1 meter. And so then our distance that we're actually going to use in our problem is going to be 0.18 meters. And our problem is F equals negative kx. And we want to find this k. I'm going to show you something. We call it the triangle. Some people call it cheating. I don't think it's cheating. I think it's knowing the resources available to you. I think it's pretty handy. So this side has the two things right next to each other, so we're going to put them on the triangle next to each other, and then the third thing is what's left. That's the force, and so we just put that on the top. We're trying to solve for the spring constant, so we're going to have negative k equals F over x. Now, you can't have your answer in negative, so you're actually going to have to put the negative on the other side. And so you'll actually end up with k equals negative F over x. So then, if you want to put your formula, you want to put your numbers in for this. Your force was negative 56 newtons, and your distance was 0.18 meters. Now you see, before I do any other math, you can see that I have newtons per meters as my unit, and that my unit for the spring constant is supposed to be newtons per meters. So as long as I can plug my answer, or plug these numbers into the calculator correctly, I can get the right answer. And I know I'm going to have the right answer because my units line up the same. And so a lot of people don't like to do the problems with the units, but I really like it because it's kind of like a check. And so if I see, before I do my plug in my numbers, if I see that the units aren't right, then I can go back and fix something. And I've done it before. I've written it just like this, and then I've multiplied the two. And if I do it, I know you probably do it. So I would always do your problems with the units. Even when you get really comfortable with it, I still do mine with the units, just to make sure they line up correctly. And so ours lined up correctly, and so I put it in the calculator, and I got negative 311.11 newtons per meters. I'm not super particular on how many decimal places you use. I like to use 2. I don't know. It's just I always try and do 2 decimal places when I can, but that does not mean that you have to do 2 decimal places. Don't feel like you have to. Okay, now part B says, how much elastic potential energy is stored in the spring when it is stretched this far? Okay, so I'm going to write it over here. We have our K was negative 311.11 newtons per meters. Our force was 56 newtons. And our distance was 0.18 meters. And our potential energy formula is 1/2 kx squared. And so if I write it here, I'm going to go ahead and put parentheses. This just reminds me when I put it into the calculator that I'm going to want to put parentheses. And I'm going to actually put 2 here. And this is just, again, like if you have a graphing calculator or something, you can put all this in at once. But in order to get the answer to come out right, you have to use this many parentheses. And so when I do that, I'm going to go ahead and do it in parts so you can kind of see what I'm doing. This should be meters. Newtons per meter. And I went ahead and I squared this part. And you can see this meters is on the bottom, and this we have a square, which means we have 2 meters up here. And so we're going to actually get negative 5.04 newtons times meter. And if you remember, the units for energy were newtons per meter, newtons times meter. So this lets us know that we plugged in everything right, or our units are right, and we set up our problem right. And so what this means, if you think about your spring, and your spring is stretched, when your spring is at the top and it's squished up like this, it has the most potential energy. Okay, this is the most potential energy. And when your spring is all the way at the bottom here, it has the least amount of potential energy. And so they're saying when you stretch your spring 0.18 meters, you're going to have a negative 5.04 joules of potential energy. And so, and that's because you're stretching it. It would have more potential energy if you had it close and squished. It would be a positive amount. Okay, but this is saying that it's lost potential energy. And so that's kind of what's going on in this one. Try your homework. Try your Hooke's Law problems and your potential energy of a spring problems. And if you have any questions, we will talk about them in class.